right. Thank you very much, Jim, for the introduction. I'm very excited to be here. It's the first year that I joined the Store Summit as a speaker. And in this session, I will talk about Snowflake Schema Data Model and what it brings to feature stores. I will be mentioning, will be talking a little bit about dimensionality and dimensional models, and also normalization. And I will be focusing more on the online store and real-time use cases, and what are the main benefits that Snowflake Schema Data Model can bring to the feature store. So let me, just as a quick recap from the previous talk from my colleague Ray, Feature Store extends the lakehouse to become an AI lakehouse. Basically, the offline store as an open lakehouse is complemented with an online store and a vector index. As you know, offline stores are commonly based on or built on columnar store. So they are more efficient or performant for historical data and contextual information, and also for time series, and they support better complex analytical queries, specifically temporal queries. And then for the online store, they are mostly built on top of row-oriented stores that provides low latency vector retrieval and real-time transformations, which are more focused on real-time cases. And as well, we have the vector index for providing similarity search on vector embeddings. So if we have a look at a common non-real-time AI lakehouse, one of the patterns that we often find is the following. We have an event bus receiving events, business events in this case, and they are consumed and transformed, and they are together with business information from operational databases combined and written to the offline store. And then from that, this data will be synchronized to the online store and the vector index. So if we look at this diagram from a data modeling perspective, we can think of business events as facts in this case, or measurements. And then the business information is basically what we can call dimensions or attributes of these measurements. And then on the offline store, normally data is organized following a dimensional data model. We see that most feature stores support star schemas, but they not many support, or it's mostly a star schema, but not a Snowflake schema. So regarding the star schema, the degree of normalization is a bit lower. Duplicated columns are allowed on the dimension tables. So there might be a little bit more redundancy in some dimension tables. So these duplicated features, and also in this case, this schema is good for offline stores in the sense that since the query engines are not optimized for joins, there is no need for using nested left joins. So the star schema works fine for these cases. And then on the other hand, if we look at the online stores, we see that online stores are primarily using key-value stores, and this is because of the scalability that they offer and the performance for primary key lookups. And basically, they can accommodate the star schema, but key-value stores can show limitations in terms of support for joins or more complex joins, and of course nested joins, and also they normally don't provide relational support for relational data models. So in the case of the search schema, for example, they can accommodate it by running iteratively primary key lookups on the dimension tables and then joining the data together. So here, at this point, what we can think of, what we can ask ourselves is the QLE store actually the best option we have for an online store? And also, can we actually benefit from using a Snowflake schema on the online store, and if we have support for relational data models? So to answer this question, basically, the first thing we need to see is to think what could be the best data model for a phyto store. So we can have a look first as OBT schemas as a first alternative, or one big table in which we have all the features and labels together in the same table. And this can work on the offline store, since we have columnar compression, and also this might work better for complex analytical queries. But when it comes to online stores when it comes to online stores that are row-based, there is no columnar compression, so data will explode, and it's not really working in this case. So another alternative would be the star schema, as I mentioned before. It works a little bit better. It provides more normalization. We will reduce redundancy in the features, and also it can work with the online store doing these iterative primary key lookups that I mentioned before. But still, we might see some redundancy in the features, duplicated features in the different dimension tables, and especially, which is what I wanted to focus today, in online cases. Using a star schema brings some new challenges, like the availability of serving keys in the online inference pipeline, which is something that we will see in the following slides. So another alternative in this case is the Snowflake schema. There is a little bit more normalization, so we reduce the redundancy of the features. So they are basically, we improve discoverability of the features and reuse of these features, and it's related to when it comes to the online inference pipelines and the serving keys that I will mention before. The Snowflake schema can basically improve the way applications enrich the request with enrich the request with contextual information. So let's have a look at an example using credit card fraud detection use case. So related to business information, we have credit card transactions. We might have the concept of fraudulent transaction, and also we will compute some aggregates on the recent activity of the credit card. And also, we will have some details about the bank accounts and the banks themselves and the merchant. So the first step here is to define the prediction problem, whether a credit card transaction is fraud or not. So in this case, we will define our label. We will identify our label and define the label feature group, which is it would be the fact table in this case. So in this case, we will pick the credit card transactions. Then with the rest of the business information, we define the dimension tables in terms of like grouping them together if they make sense semantically, like features that relate to bank accounts together and so on. So after doing that, if we take into account the star schema, if we decide to organize our tables following a star schema data model, we will have the transactions table in the middle, and then we will have foreign keys or surrogate keys pointing to these dimension tables. Then when it comes to online inference pipelines, things get a little bit trickier. So in the ideal world, if we have an application that tries to detect if a transaction is fraud or not, when the transaction is being processed, the application will use a transaction ID and try to retrieve related information to the bank details and recent activity of the credit card and so on. But in the real world, the transaction has not happened yet. So this transaction is not available at prediction time. So therefore, you cannot retrieve the value using just the transaction ID. In this case, the application would need all the foreign keys to retrieve the corresponding data to enrich the request and before passing it to the model. So this is the first problem. One alternative to fix this problem would be if we decide to create a mapping table, for example, that basically maps the transaction ID with the foreign keys, and then the application could use the transaction ID to get the rest of the keys, and then you can retrieve the corresponding data from the dimension tables. But then the second problem appears, which is you will have to handle or maintain additional ETL jobs to basically keep this mapping table up to date. So it's not really a solution. And then another approach would be if you decide to denormalize the credit card transaction table, the one with recent activity with the aggregations. If you decide to duplicate some of the features from the other dimension tables and added them to this table, then the application can basically retrieve all the features at once using the credit card number in this case. But the problem here again is first you have duplicated columns, and then also it means that you will need still to use additional ETL jobs to maintain the denormalized tables. So you have to update the features in all the places that you're using it. So what about the Snowflake Schema Data Model? If we decide to organize our data following this schema, again, we will have the transactions table as the fact table, and then we will have a foreign key to the merchant's details, and then a foreign key to the aggregates or recent information, recent activity of the credit card that contains a foreign key to bank details and another foreign key to the bank account details. So in this case, we again see at the have a look at the online inference pipeline. We see that the application just needs to know the credit card number and also the merchant ID. The application does not need to know the bank ID or the account ID. So in this case, we basically are reducing the number of serving keys that the application needs to know at prediction time, and also no additional ETL jobs are needed to maintain duplicated features or additional dimension tables. So now, how we support Snowflake Schema Data Model in Hopsworks. Basically, in Hopsworks, we use RunDB as our online store. RunDB is a in-memory distributed key-value store with SQL capabilities, so it supports relational data models, and also there are some optimizations when it comes to projection push down and push down of left joins and also left nested joins. We have some peer review results that we published in our research paper at SIGMOD this year, where we have some numbers here. So we compare how push down left joins perform compared to iterative primary key lookups, and also comparison between star schema data model and Snowflake schema data model. And we saw that basically for the star schema, we can reach a reduction of 30 to 50% in latencies, and also an increase between 50 to 200 in throughput. And when it comes to the Snowflake schema, the reduction is a little bit less, it's 20 to 40 compared to the 30 to 50 for the star schema. And for the throughput is more or less the same. So the point here is that if you use a star schema or the Snowflake schema, they show comparable results, and they basically perform much better than if you do iterative primary key lookups. Yeah, so if you have, if you want to dig a little bit deeper on the experiments or how they were performed and explanation of the push down left join, so feel free to get access to the research paper. And also another benchmark that we did was related to feature vector retrieval, where we compared the performance between another two cloud feature stores. And basically we compared the feature retrieval with different batch sizes. And for example, using batch size 1, a single vector lookup, we see that for P99, we reached between 15% to 11% less latencies. So this is the last slide, I think. So when it comes to data modeling using the Hopsworks, the data modeling in Hopsworks, you can use the Python API that we provide different classes for the different abstractions like feature groups, feature views, and so on. So you can get the different feature groups. And if you see on the left, this is the way you could create the query, the nested join for the Snowflake schema. So you basically, starting from the label, which is will be the left most feature group, you start selecting the features and joining them with the other tables. And the Hopsworks optimizer will know which are the primary keys and foreign keys to do the joins. And then on the right side, you can see how the star schema could be implemented. Then you can create a feature view, basically calling the create feature view method and passing the query, specifying which is the label. And then when it comes to retrieving feature vectors in the online inference pipeline, as you see on the left hand side, you need to provide less serving API keys because you're using the Snowflake schema. And on the right side, you can see that you need to provide the bank ID and the merchant ID as well. So this is all for today. I hope you find it interesting. And also, if you have any doubts related to the implementations or benchmarks, feel free to have a look at the research paper. Also, there is the feature store benchmarks that are open source and public. And also, the last thing, the star schema and the Snowflake schema data models are also explained in the book that Jim Dowling is writing. So thank you for listening.